The XF-84 earned its nickname Thunderscreech for good reason. It stands as the loudest aircraft ever created, generating sound waves so powerful they could be heard from 25 miles away. Indeed, this experimental aircraft supersonic propeller tips, rotating at an astounding Mach 118, created a continuous sonic boom that proved devastating for ground crews. The noise was so intense that it caused severe nausea and headaches, and in one documented case, triggered a seizure in an engineer exposed to its full force, powered by a massive 5,850 HP turboprop engine with afterburner capability, reaching 7,230 HP. The XF-84 represented an ambitious leap in aviation engineering. However, despite its impressive specifications and innovative design features, including a 12-foot diameter propeller with 3 steel blades, the aircraft's operational history was remarkably brief. The 2 prototypes completed only 12 test flights, accumulating less than 7 hours of total flight time before the project's cancellation in 1956. This video will explore the fascinating engineering journey of the Thunderscreech, from its ambitious design goals to the technical challenges that ultimately led to its downfall. The birth of the XF-84 Thunderscreech project. The 1950s marked an unprecedented period of aviation advancement as the industry emerged from World War II as the largest manufacturing sector in the United States. During the 62 months between July 1940 and August 1945, American manufacturers produced nearly 300,000 aircraft, establishing a foundation for post-war innovation. The aviation landscape underwent a significant transformation after World War II. The military services were reorganized in 1947, establishing the United States Air Force as a separate service. Furthermore, the industry faced mounting pressure to develop aircraft combining the emerging capabilities of jet engines with traditional propeller-driven benefits. Republic Aviation launched Project 3347 in response to these evolving needs. Initially designated as the S-106, the project was subsequently renamed to XF-84 to maintain its connection with the F-80 for Thunderscreech lineage. The development marked a bold effort to design an aircraft capable of achieving several seemingly contradictory objectives, including jet-like performance, extended operational range, reduced fuel consumption, and lower landing speeds. The project originated from a U.S. Navy requirement for a carrier-based fighter that could operate without catapult assistance. The Air Force's Wright Air Development Center became a key sponsor, recognizing the potential for a versatile aircraft that could serve multiple roles. The initial specifications called for an aircraft powered by a 5,850 HP Allison XT40-1 turboprop engine. Additionally, the design incorporated an afterburner capability that could increase power output to 7,230 HP. The engineering team faced the complex challenge of integrating these powerful components while maintaining stable flight characteristics. The project's ambitious scope reflected the era's optimistic approach to technological advancement. Although the Navy initially ordered 3 prototypes, they subsequently canceled their participation, consequently transforming the remaining XF-84 prototypes into research aircraft for the Air Force's Propeller Laboratory at Wright-Patterson AFB. Engineering marvel, the supersonic propeller design. First of all, the engineering team at Republic Aviation faced unprecedented challenges in designing a propeller that could operate efficiently at supersonic speeds. The resulting 3-bladed aero product's propeller represented a significant advancement in aviation technology, specifically engineered to maintain stability at extreme velocities. The engineering team created a robust propeller design with square-tipped steel blades spanning 12 feet, equivalent to 3.7 meters in diameter, These blades feature thin profiles optimized for supersonic speeds and were constructed from specialized high-strength steel capable of withstanding immense rotational forces, with a tensile strength rated at 180,000 pounds per square inch. The propeller's thrust control system operated through an innovative variable pitch mechanism. Accordingly, the blade pitch could be adjusted while maintaining a constant rotational speed of 3,000 rpm. This design choice enabled precise thrust control without altering the engine's power output. The blade design demanded a precise balance among competing factors, guided by a specialized table of specifications. The blade tips were designed to achieve a velocity of Mach 1.18 to maximize thrust generation, while the chord design incorporated a wide chord, low aspect ratio configuration to ensure stability at supersonic speeds. Additionally, the blade profile featured extremely thin sections to minimize shock formation. Moreover, the engineering team incorporated advanced aerodynamic principles to address the challenges of supersonic propeller operation. The blade sections were designed to maintain optimal lift-drag ratios at high speeds. Therefore, each blade segment operated at carefully calculated angles to maximize efficiency while minimizing the formation of shock waves. The design process required extensive analysis of blade section, interference, and shock field interactions at supersonic speeds. The engineering team achieved remarkable results, with theoretical calculations suggesting potential efficiency rates of 70% at tip Mach numbers reaching 2.3. Power system integration. At the heart of the XF84 lay an innovative power system built around the Allison XT40-1 turboprop engine. This power plant represented a significant departure from conventional designs, particularly in its unique configuration and integration challenges. The XT40-1 engine represented a groundbreaking innovation in aviation propulsion, showcasing a revolutionary design that paired to T38 gas turbine power sections mounted side by side. This unique dual turbine configuration produced an extraordinary 5,850 shaft horsepower, positioning it as one of the most powerful engines of its time. Each T38 turbine was equipped with a highly efficient 19-stage axial flow compressor, contributing to the engine's remarkable performance capabilities. Additionally, the XT40-1 delivered 1,296 pounds of jet thrust, while maintaining a total weight of 2,860 pounds, reflecting its sophisticated and efficient engineering. A particularly notable feature of this engine was its integrated afterburner capability, designed to further enhance its output to an impressive 7,400 horsepower. However, this feature, despite its potential, was never subjected to flight testing. The XT40-1 thus stood as a testament to advanced engineering, blending innovation and performance in a compact, high-powered design. The power transmission system was designed with several innovative features to enhance efficiency and reliability. It utilized a common reduction gearbox that connected both turbines, allowing for synchronized operation. The design included 18-foot-long propeller shafts and a single-stage herringbone gear set, which ensured smooth power transfer while minimizing vibration and wear. Additionally, specialized overrunning clutches were integrated into the system, providing an added layer of functionality and protection during operation. Nevertheless, the integration of this powerful system presented significant operational hurdles. The entire aircraft tended to rotate around the prop shaft, with the airframe turning left while the propeller spun right. Since reliability proved problematic, the engineers incorporated a retractable ram-to-air turbine, the first aircraft to feature such a system. This backup power source would automatically deploy into the airstream whenever the landing gear extended, providing essential hydraulic and electrical power during emergencies. The system's complexity manifested in several operational limitations. Particularly concerning was the mandatory 30 minute warm-up period required before each flight. This extended preparation time, coupled with frequent mechanical failures, severely limited the aircraft's practical utility. Engine failures caused by propeller vibrations ended 10 out of 11 test flights. The power system's integration challenges ultimately proved insurmountable. The combination of mechanical difficulties with the prop pitch gearing and severe vibrations generated by the lengthy propeller shafts led to persistent reliability issues. These technical hurdles, rather than any single catastrophic failure, contributed significantly to the project's eventual termination. Technical specifications and performance. The Republic XF-84's Thunderscreech represented a remarkable combination of size and power specifications that set it apart from conventional aircraft of its era. First of all, the aircraft's physical dimensions were carefully engineered to balance performance with practical operational requirements. The XF-84 was a sizable aircraft, with a length of 51 feet 5 inches, a wingspan of 33 feet 5 inches, and a height of 15 feet 4 inches. Its wing area measured 331.0 square feet, providing ample surface area for lift generation. Notwithstanding its substantial size, the aircraft maintained a relatively efficient weight distribution. The empty weight stood at 17,892 pounds, as a result of careful material selection and structural engineering. At maximum capacity, the gross weight reached 27,046 pounds. The speed and altitude capabilities of the XF-84 reflected a blend of ambition and compromise, as its actual performance did not fully align with its designers' lofty expectations. Republic Aviation initially predicted a maximum speed of 670 miles per hour, which would have secured its position as the fastest propeller-driven aircraft ever constructed. However, real-world performance testing revealed a maximum speed of 520 miles per hour, falling significantly short of that anticipated figure. This discrepancy highlighted the challenges of pushing the boundaries of propeller-driven flight at near transonic speeds. While its speed capabilities were underwhelmed, the XF-84 demonstrated noteworthy performance in terms of altitude. It achieved a service ceiling of 40,000 feet, showcasing its ability to operate effectively at high altitudes. Additionally, the aircraft boasted a robust rate of climb, capable of ascending 5,000 feet per minute, underscoring its impressive vertical performance. These attributes reflected the advanced engineering that went into its design, even if the aircraft did not achieve the groundbreaking speeds originally envisioned. The XF-84's operational range exceeded 2,000 miles, marking a significant achievement in terms of fuel efficiency for its era. This extended range capability aligned with the original project goal of combining jet fighter performance with propeller-driven efficiency. The Allison XT-40-1 turboprop engine, rated at 5,850 horsepower, theoretically offered the potential for increased power output to 7,400 HP with afterburner engagement. Ultimately, the afterburner capability remained untested during flight operations, leaving questions about potential performance improvements unanswered. The thrust-to-weight ratio of 0.66 highlighted the aircraft's unique position between conventional propeller-driven aircraft and pure jet fighters. This characteristic underscored the experimental nature of the project and its attempt to bridge the gap between traditional and emerging aviation technologies. The XF-84 sound phenomenon. First and foremost, the Republic XF-84's most distinctive characteristic was its extraordinary sound generation capabilities. The aircraft's unique acoustic signature stemmed from its revolutionary propeller design, which created unprecedented sound phenomena in aviation history. The supersonic propeller tips, rotating at Mach 1.18, generated a continuous sonic boom that radiated laterally from the propellers for hundreds of yards. The outer 24 to 30 inches of the propeller blades maintained supersonic speeds even during idle thrust. The constant supersonic rotation of the propeller generated a distinctive sound pattern, characterized by lateral radiation from the blades. This powerful noise was audible over an impressive range, reaching up to 25 miles. The propeller tips reach speeds of Mach 1.18, with the outer 61 to 76 centimeters of the blades operating in the supersonic range. This combination of speed and sound propagation contributed to the aircraft's highly unique acoustic signature. In addition to the primary sonic boom, the aircraft generated complex sound patterns from multiple sources. Notably, no official decibel measurements were ever recorded. As test pilot Henry Beard remarked, "Nobody ever actually recorded the decibels. I think they were afraid the measuring device might get broken." The sound intensity of the aircraft was driven by three main factors: the shock waves produced by the supersonic propeller tips, the noise generated by the subsonic sections of the blades, and the combined sound output from the dual turbine sections. The sound effects on ground personnel were so severe that they necessitated substantial operational adjustments. The intense noise caused physical issues such as severe nausea and headaches among ground crews, with some individuals even experiencing seizures due to prolonged exposure. The vibrations generated by the sound posed a risk of damaging sensitive control tower components, while the overwhelming noise made it impossible to maintain standard communication protocols. The sound intensity became so problematic that Edwards Air Force Base implemented extraordinary measures. Base personnel resorted to using signal flags and lights for communication. Ultimately, after numerous complaints, the Air Force Flight Test Center mandated the aircraft's relocation to Rogers Dry Lake, far from the flight line, for engine testing. One particularly notable incident involved a C-47 crew chief who was severely incapacitated during a 30-minute ground run while inside his aircraft. The shock waves proved powerful enough to physically knock down personnel who ventured too close to the propeller's plane of rotation. The sound phenomenon fundamentally altered standard operating procedures at Edwards AFB. The control tower staff faced potential damage to sensitive equipment, forcing them to develop alternative communication methods with ground crews. This unprecedented situation highlighted the practical limitations of operating such an acoustically intense aircraft within standard military facilities. Flight testing program. The testing program of the XF-84 began after its transportation via rail from Republic's Farmingdale plant to Edwards Air Force Base. The program would ultimately prove to be one of the shortest yet most eventful in experimental aircraft history. Ground testing revealed immediate challenges that would plague the entire program. The aircraft required an extensive 30-minute warm-up period before each flight, creating significant operational limitations. The ground crews faced unprecedented difficulties, primarily due to the intense sonic effects that disrupted normal base operations. The XF-84 made its historic first flight on July 22, 1955, marking the beginning of an ambitious testing program. Throughout the testing phase, a total of 12 flights were conducted, accumulating 6 hours and 40 minutes of flight time. However, despite the aircraft's potential, the results were far from ideal. Out of the 12 flights, only one was considered a complete success, illustrating the significant challenges faced by the testing team. The two prototypes had different flight distributions, with Prototype 1 completing 8 flights and Prototype 2 finishing 4. The testing phase uncovered some critical issues that severely hindered the aircraft's performance. One of the major problems was persistent mechanical failures in the propeller pitch gearing, which directly impacted the aircraft's ability to maintain stable performance. Additionally, the XF-84 suffered from severe airframe vibrations that further complicated its handling and reliability. Frequent engine malfunctions also plagued the aircraft, preventing it from reaching its full potential during flight. Lastly, the aircraft exhibited unstable longitudinal control. making it difficult to manage and navigate under certain conditions. These challenges highlighted the difficulties in achieving the ambitious design goals set for the XF-84 despite its groundbreaking engineering. Two test pilots, Hank Beard and Lynn Hendricks, undertook the challenging task of flying the Thunderscreech. Beard conducted 11 of the 12 test flights, yet 10 of his flights concluded with forced landings. The aircraft's performance limitations became evident when it demonstrated an unhappy practice of snaking at speeds above 450 knots, indicating serious longitudinal stability issues. Lynn Hendricks' experience proved notably dramatic. After his single flight attempt, he famously declared to Republic's chief engineer, "You aren't big enough, and there aren't enough of you to get me in that thing again." His refusal to conduct further flights stemmed from the aircraft's dangerous handling characteristics at higher speeds. The testing program never progressed beyond the manufacturer's phase, approving flights. The Air Force Flight Test Center, recognizing the mounting technical challenges, directed the Republic to conduct engine runs far from the flight line on Rogers Dry Lake. Yet, these precautions did little to salvage the program's viability. The combination of mechanical failures, control issues, and operational impracticality led to the program's termination in September 1956. The aircraft's inability to reach its design speeds, coupled with persistent stability problems, demonstrated that the ambitious concept of a supersonic propeller-driven fighter had reached its practical limits. Engineering modifications and improvements throughout the XF-84's development, Republic Aviation implemented numerous engineering modifications to address the aircraft's inherent challenges. These changes ranged from fundamental structural alterations to innovative system implementations, each aimed at improving the aircraft's performance and operational capabilities. The engineering team made several critical modifications to counter the intense torque generated by the supersonic propeller. Notably, they raised the horizontal tail surfaces to a position atop the tail fin, ensuring clearance from the devastating prop wash effects. A distinctive triangular shark fin was installed behind the cockpit to enhance stability during flight operations. Several structural modifications were made to address the aircraft's performance issues. The left leading edge intake was extended 12 inches forward in comparison to the right side to improve airflow and balance. Additionally, differential operation capabilities were introduced for the left and right flaps, allowing for more precise control. To further enhance the aircraft's stability and handling, a T-tail configuration was implemented, providing improved control surfaces. Efforts to reduce the aircraft's notorious noise issues were a primary focus for engineers, who implemented a series of strategies aimed at mitigating the acoustic impact. One of the most significant areas of modification was the engine placement to minimize the disruptive effects on ground personnel and surrounding infrastructure. While this modification did help reduce some of the noise experienced on the ground, its success was limited, as the aircraft still produced a substantial sound level during operation. In addition, efforts were made to reduce base disruption by relocating the aircraft's operations to Rogers Dry Lake, a more remote area that allowed for flight testing with less impact on populated regions. While this move helped to lessen the effects on the immediate surroundings, it did not fully resolve the noise problem. Another key aspect of the noise reduction strategy involved optimizing the blade configuration to improve the sonic characteristics of the propeller. Engineers tested multiple designs in an attempt to refine the blade's shape and minimize the intense noise generated by supersonic rotation. Despite these efforts, the aircraft continued to present significant challenges in achieving a level of noise control that would make it suitable for regular operation. The engineering team introduced several innovative features to enhance the aircraft's capabilities. Among these was the pioneering implementation of a retractable ram-to-air turbine designed to deploy automatically whenever the landing gear extended. This system proved invaluable, providing crucial electrical and hydraulic power during the frequent engine failures that plagued the aircraft. Meanwhile, the integration of an afterburner system aimed to boost the engine's output from 5,850 HP to 7,400 HP. This modification, theoretically, would have enabled supersonic flight with the propeller in a feathered position. Ultimately, the program concluded before the afterburner could be tested in flight. The engineering team tackled multiple mechanical challenges concurrently, focusing on improving key systems. In the case of the propeller pitch control system, they implemented advanced gearing mechanisms and modified the control systems to enhance reliability. Additionally, safety features were incorporated to better handle emergencies, ensuring the aircraft could be managed in critical scenarios. Meanwhile, the drive system underwent significant modifications, including reinforcing the 18-foot-long propeller shafts and refining the gearbox design. The modifications, while innovative, faced persistent challenges. The aircraft continued experiencing severe vibrations at speeds exceeding 450 mph. These vibrations, originating from the propeller shafts, created cascading effects throughout the airframe. The engineering team's efforts to resolve these issues through structural reinforcement and system optimizations proved insufficient to overcome the fundamental design limitations. The extensive modifications required for operational capability highlighted the project's inherent complexities. Each improvement attempt revealed new challenges, creating a cycle of continuous engineering adjustments. The aircraft's mechanical difficulties persisted, with 11 out of its 12 test flights ending in engine failures, underscoring the limitations of the available technology and engineering solutions of that era. Project Termination and lessons learned. In September 1956, the United States Air Force officially terminated the XF-84's Thunderscreech program, marking the end of an ambitious yet troubled chapter in aviation history. The project's conclusion stemmed from a combination of insurmountable technical challenges and operational limitations that proved too significant to overcome. The XF-84's operational history revealed severe technical constraints that ultimately sealed its fate. Out of 12 test flights, 10 ended in emergency landings due to mechanical failures. The aircraft encountered several critical issues during its testing phase. Engine failures were a major concern, with 10 out of 11 test flights being prematurely terminated due to these malfunctions. Additionally, the aircraft required a lengthy 30-minute warm-up time before each flight, which proved to be an operational challenge. Speed limitations also became evident, as the aircraft was never able to exceed 450 knots, falling short of its design expectations. Furthermore, stability issues emerged, particularly at high speeds, where the aircraft experienced severe snaking, making it difficult to maintain stable flight. The propeller's supersonic rotation, operating at Mach 118, generated devastating vibrations that affected both the airframe and nearby structures. Markedly, these vibrations proved so severe that they threatened to damage sensitive equipment in the Edwards AFB control tower. The operational assessment of the XF-84 revealed substantial drawbacks that outweighed its potential benefits. Primarily, the aircraft's extensive maintenance requirements and poor reliability made it impractical for military service. Several factors led to the aircraft's unfavorable evaluation. The extended preparation time, which conflicted with the need for rapid deployment, proved to be a significant drawback. Additionally, the high maintenance demands placed a strain on operational costs, as frequent repairs were necessary due to persistent mechanical issues. Furthermore, safety concerns for ground personnel, stemming from the aircraft's intense noise and vibrations, limited its operational flexibility and further hindered its practicality in real-world scenarios. Notably, the XF-84's project, despite its shortcomings, contributed valuable insights to aviation technology. The program led to several significant advancements in aviation technology. It marked the first use of a ram air turbine system on an aircraft, a pioneering development at the time. The advanced air brake design, developed for the XF-84 was later adapted for use on the F-105 Thunderscreech, contributing to improved performance in subsequent aircraft. Additionally, the program provided groundbreaking research in supersonic propeller technology, offering valuable insights into the challenges of operating at such high speeds. The program also generated crucial data on noise suppression and vibration control, which would influence future aircraft designs and operational strategies. Undeniably, the project's technical challenges provided crucial lessons for future aircraft development. The engineering team's experience with supersonic propeller design and noise management informed subsequent aviation projects. The aircraft's limitations straightaway demonstrated the practical boundaries of propeller-driven fighter technology. The program's termination influenced the Pentagon's strategic direction as they permanently moved away from propeller-driven fighters. This decisive shift toward jet propulsion marked a turning point in military aviation development. The XF-84's legacy serves as a reminder that innovation often comes at the cost of practical limitations and unforeseen challenges. The conclusion of the project provided valuable engineering insights into several critical areas. It highlighted the limitations of propeller design at supersonic speeds, revealing the challenges in optimizing performance at such high velocities. The project also underscored the structural requirements for installing high-power turboprop systems, offering a deeper understanding of the stresses and demands placed on the airframe. Additionally, it contributed to the knowledge of noise and vibration management in high-performance aircraft, addressing the need for effective control in such environments. Finally, the project shed light on the integration challenges associated with complex power transmission systems, offering important lessons for future aircraft designs. Republic Aviation's chief engineer characterized the XT-40 engine as a monstrosity, a mechanical nightmare, reflecting the fundamental challenges faced in pushing the boundaries of propeller-driven technology. The XF-84's development cycle demonstrated that theoretical possibilities do not always translate into practical applications, particularly when operational requirements demand reliability and ease of maintenance. The Republic XF-84's Thunderscreech is a fascinating example of 1950 aviation ambition. Designed to break barriers with its supersonic propeller, it ultimately became infamous for its overwhelming noise and relentless mechanical failures, forcing its early retirement after just 12 flights. Though it never succeeded as a fighter, its pioneering innovations, like the first ram air turbine system, left a lasting mark on future aircraft design. What do you think about this daring piece of aviation history? Please share your thoughts about this plane in the comments section. Thank you for watching.